learners, I welcome you all to the first module, that is Fundamentals of Electricity of the SWAYAM MOOC on Electricity and Electrical Wiring. I am Dr. Smriti Mala Sharma, Assistant Professor in Physics, B. Borua College, Guwahati. Module 1 has been divided into 3 units. In Unit 1 and 2, you have learned about understanding electricity and basic terms related to electricity. Here we have covered electrical energy, sources of electricity, atomic structure, principles of current flow, and basic terms of electricity. In the third unit of this module, we will discuss about conductors and insulators. So here we will focus on introduction to conductors and insulators, their examples, properties, their energy band diagrams, types, advantages, disadvantages, and applications. Let us first discuss what are the conductors. Conductors are the materials that allow current to flow through them. In other words, we can say the materials through which an electric surge can flow are called conductors. Then how to measure the effectiveness of a conductor? The effectiveness of a conductor is measured with the help of electrical conductivity, which measures how quickly electrons may move through the substance. Most metals allow electric current to flow through them easily because they have low resistance. The process of electrical current flowing through a wire is called conduction, and the ability to conduct electric current is called electrical conductivity. Conductivity is the inverse of resistivity. The SI unit for electrical resistivity is ohm meter. Then what is 1 ohm meter? 1 ohm meter is defined as the unit of resistivity of the conductor with a length of 1 meter and a cross-sectional area of 1 square meter. Resistivity is the value that characterizes a given material. However, it is affected by temperature. Resistivity is commonly represented by Greek letter rho. So the relation between the resistivity and resistance is given by the following equation. You can see this equation. Here, rho is resistivity, R is resistance, S is cross-sectional area of the material, and L is the length of the material under consideration. The inverse of resistivity is conductivity, and SI unit for conductivity is Siemens per meter. Now, the question is, why do metals conduct? To answer this question, let us understand the atomic structure of metals. So here we can see the atomic structure of a metal, in which we can see that electrons orbit nuclei inside the atoms. They cannot escape because the negatively charged electrons are attracted to the positively charged nucleus by strong electrostatic forces. The electrons are bound to the nucleus. In metals, since the outer electrons orbit further from the nucleus, the forces binding them are weaker. The forces on these outer electrons are weak, and thus the electrons can move relatively freely from atom to atom. These are called the free electrons or delocalized electrons. Materials with many free electrons, such as metals, are good electrical conductors because these free electrons can flow through the metal when a potential difference is applied. Metals with more free electrons like copper or silver are the best conductors because they have least resistance. Metals with fewer free electrons like lead or tin have higher resistance, so they don't conduct as well. Aluminium is an example of a very good electrical conductor because it has many free electrons which can flow through the metal. Besides this, copper, silver, gold, graphite, platinum, water, and the human body are examples of very good conductors of electricity. Now let us discuss the properties of a conductor. In equilibrium condition, a conductor exhibits some very important properties. For example, a conductor always allows the movement of electrons and ions through them. The electric field inside a conductor is zero, allowing the electrons to flow within them. The charge density inside a conductor is zero. Only on the surface of the conductor, the free electrons or free charges can exist. All points of a conductor are at the same potential. So, dear learners, these are the properties of a good conductor. Next, we will move to the energy band diagram of a conductor. In case of the conductors, the energy gap between the valence band and conduction band is almost zero. Thus, the valence band and conduction band overlap each other. Due to this overlapping, electrons can easily flow from valence band to conduction band and contribute to electrical conductivity. Conductors can be classified into different types. For example, metallic conductors. These are the conductors made of metals or alloys that have high conductivity due to their free electrons. They are widely used for wiring, transmission lines, electrical machines, electrical contacts, etc. Some examples of metallic conductors are silver, copper, aluminium, iron, etc. Next, we can go for ionic conductors. These are the conductors made of ionic compounds that have high conductivity due to their free ions when they are dissolved in water or melted in liquid state. They are used in electrolysis, batteries, fuel cells, etc. Some of the examples are sodium chloride, potassium hydroxide, sulfuric acid. Again, we can go for the molecular conductors. These are conductors made of molecules that have high conductivity due to their delocalized electrons or molecular orbitals that can overlap with each other. They are used for organic electronics, nanotechnology, etc. Some of the examples are graphite, carbon nanotube, polyacetylene, etc. Next, we have another type of conductor which are said to be superconductors. These are the conductors that have zero resistance and infinite conductivity whenever they are cooled below a certain critical temperature. They also exhibit some phenomenon like Meister effect, in which we see that expulsion of magnetic field below the critical temperature. They are used for superconducting magnets, quantum computers, medical imaging, etc. Some examples of very good superconductors are mercury, lead, yttrium, barium, copper oxide, etc. Electrical conductors are also categorized by their ohmic response. They can be classified as ohmic and non-ohmic conductors. Ohmic conductors are materials that follow Ohm's law for any potential difference in temperature. They have a linear relationship between voltage and current, which means their resistance is constant. Most metals are ohmic conductors at normal conditions, for example, silver, copper, aluminium, iron, etc. And in case of non-ohmic conductors, they are the materials that don't follow Ohm's law for any potential difference or temperature. They have a non-linear relationship between voltage and current, which means their resistance varies with the applied voltage. Non-ohmic conductors may exhibit negative resistance where the current decreases as the voltage increases, or positive resistance where the current increases as the voltage increases. But the proportionality is not there. Some non-ohmic conductors may also have threshold voltage, below which no current flows. Examples of non-ohmic conductors are the diodes, light bulbs, thermistors, LDRs, etc. Electrical conductors can also be classified on the basis of their physical state and composition. Here are some examples of electrical conductors in different categories. For example, in case of solid conductors, the materials that we use have a fixed shape and a volume. They can be further divided into metallic and non-metallic conductors. Metallic conductors are metals or metal alloys that have high conductivity and low resistivity. They have a lattice structure of positive ions surrounded by a sea of free electrons. Some of the metallic conductors are silver, copper, gold, aluminium, iron, brass, bronze, etc. Non-metallic conductors are non-metals that have some free electrons or ions in their structure. They have lower conductivity and higher resistivity than metals. Some of the examples are graphite, carbon nanotubes, graphene, etc. Then if we go for the liquid conductors are materials that have no fixed shape but a fixed volume. They can be further divided into metallic and non-metallic conductors. Metallic liquid conductors are metals that are in a liquid state at room temperature or when heated. They have high conductivity and low resistivity. They have a similar structure to solid metal but with a more interatomic spacing and mobility. An example of a metallic liquid conductor is mercury. Non-metallic liquid conductors are liquid that contain dissolved ions or molecules that can carry a charge. They have lower conductivity and higher resistivity than metals. They have a structure of polar or ionic solutes in a solvent. Some examples of non-metallic liquid conductors are salt water, acid solution, electrolytes. Now we'll go for the factors that affect conductivity of an electrical conductor. The conductivity of an electrical conductor depends upon several factors. It depends upon type and number of free charge carriers present in the material. It depends upon the size and shape of the conductor. It is dependent on the temperature of the conductor. It depends on the presence of impurities and defect in the conductor. It also depends upon the frequency of the applied electric field. Next, we are moving to the advantages of an electrical conductor. In case of electrical conductor, electrical resistance is low, its electrical conductivity is high, it has low cost, and its thermal stability is high. If we go to the disadvantages of electrical conductor, it is highly sensitive to any type of corrosion, it is highly sensitive to mechanical stress, it is highly sensitive to temperature changes, and it is sensitive to electromagnetic interference. Now we are moving to the applications of electrical conductors. So electrical conductors have many applications in our day-to-day life. They find applications in wirings, transmission lines, electrical machines, heating elements. They can also find applications in electrostatic shielding and electrical sensors. So dear learners, as we have come to the end of the discussion on conductors, let us test our learning by attempting the following questions. So you have the first question. Aluminium is, your options are bad conductor, good conductor, non-metal, superconductor. So what may be the answer for this? So the answer is aluminium is a good conductor. Next we'll move to the second question. The second question is, a material that has zero resistance is called, the options are insulator, conductor, superconductor or semiconductor. So the answer is, it is a superconductor. Our third question is, what is the inverse of resistance called? The options are inductance, conductance, resistivity or permittivity. So the answer is conductance. Our fourth question is, why is copper a preferred choice in making electrical wires? Options are, copper is a good conductor of electricity, it is poor conductor of electricity, it is a good insulator, it is a good superconductor. So the answer is, copper is a very good conductor of electricity. Our last question in the conductor part is that good conductors have many loosely bound. The options are atoms, protons, molecules, electrons, and the answer is electrons. Dear learners, hope you have enjoyed the small quiz. Let us move to the next topic of today. The topic is, what is an insulator? So what is an insulator? A substance in which the electrical current cannot flow easily is referred to as an electrical insulator. In case of insulator, the electrons in the atom are immobile and they are strongly bonded. Simply, the insulators don't have the free electrons to move in their valence shell. Electric current can flow more freely through conductors and semiconductors than the other materials like insulators. Insulators can be identified by its resistivity, which is higher than that of semiconductors or conductors. Most of the non-metals are considered to be insulators. The most common examples of insulators are plastic, wax, rubber, glass, bakelite, ceramics, mica, porcelain, quartz, etc. The concept of valence band theory explains the behavior of electrical insulators. According to this theory, an insulator's valence band and conduction band are separated by a white space known as the forbidden band. No electrons can travel up to the conduction band because the valence band is completely filled. The conduction band is thus vacant. Since there are no electrons in an insulator's conduction band, the substance cannot conduct electricity because only the electrons in a conduction band can flow with ease. As a result, such materials are termed as electrical insulators. If we observe the electronic structure of neon atom, we see that it has 8 electrons in the outermost orbit. Hence, it is stable and it can be considered as a good insulator. We are moving to the properties of electrical insulators. Some insulators do not conduct electricity due to the absence of free electrons. The valence electrons in electrical insulators are tightly bound together. Electrical insulators have high resistivity. They have high value of dielectric constant or dielectric strength. Their electrically insulating materials have high permeability towards air. They have varied values of breakdown voltage according to the material, which makes them choices in electrical insulations. So now we can move to the types of electrical insulators. So electrical insulators can be classified to different types. On the basis of the type of material we are using, the insulators can be classified as organic insulators. The organic insulators are made from natural or synthetic organic compounds, for example, rubber, plastic, resin, etc. They can be classified into inorganic insulators, which are made from inorganic materials such as ceramics, glass, and porcelain. On the basis of dielectric constant, the insulators can be classified as high dielectric constant insulators and low dielectric constant insulators. In case of high dielectric constant insulators, they have higher ability to store electrical energy under any electric field such as ceramics and certain polymers. In case of low dielectric constant insulators, these materials have a lower ability to store electrical energy and are often used for their thermal properties as well, such as glass and certain plastics. On the basis of application, the insulators can be classified as high voltage insulators and low voltage insulators. In case of high voltage insulators, these materials are designed to withstand high voltages without breakdown. Examples include ceramic and glass insulators used in power transmission lines. In case of low voltage insulators, these are the materials which are used in low voltage applications where robust insulation is still required but not as extreme as high voltage applications. Depending upon the temperature resistance, the insulators can be divided into thermosetting plastics and thermoplastics. In case of thermosetting plastics, the materials are resistant to high temperature, do not soften upon heating. And in case of thermoplastics, the insulators can soften and reform upon heating, offering flexibility in manufacturing. If we go to the design and shape of the insulators, they can be classified into different types. For example, solid insulators, they are made of single piece of material like rods, sheets or blocks. In case of composite insulators, they are made of different materials combined to achieve specific properties such as fiberglass, reinforced plastic, etc. In the transmission and power distribution systems, 6 different types of insulators are used. Each insulator can have multiple insulating discs. If one disc can sustain an 11 kV voltage capacity and 6 discs can sustain a 66 kV voltage, these 6 types of insulators are selected on the basis of operating voltage ratings. They are pin insulator, suspension insulator, strain insulator, stackle insulator, post insulator, and stay insulator. So in case of pin insulator, the pin type of insulators are mostly used in the distribution system. Pin insulators can sustain up to 11 kV voltage capacity. It is made up of material that has high mechanical strength. It can be connected with horizontal as well as vertical positions. This type of insulator is used in the high voltage overhead distribution line. In case of suspension insulator, the insulator is also said to be disc insulator. Mostly, the suspension insulator is made of glass or porcelain insulating materials. Especially, glass type of insulators used in lightweight condition. The voltage operating capacity in case of suspension insulator is from 11 kV to 760 kV. It is mostly used in the overhead transmission system or line. It provides more flexibility to the overhead line. In case of strain insulator, the strain insulator is similar to suspension insulator type. Like a suspension insulator, a strain insulator can be used in the overhead transmission line, but it has slightly different specification and the working loads. It is used in higher voltage conditions, that is above 33 kV. Primarily, it is used in the band or arm places of the transmission lines. Next, we'll move to the cycle insulator. In case of cycle insulator occurs in small size on the overhead distribution system. In the distribution line, the metallic strip is used to connect the cycle insulator. In case of post insulator, they are commonly used in the substation or generating substation. In a substation, it is suitable for different voltage levels. Always it is placed in a vertical position. It helps to protect switch gear, transformers and other connecting devices. This type of insulator has strong mechanical strength. The last insulator is the stay insulator. This stay insulator is known as the egg insulator because it looks like an oval or rectangular shape. Stay insulator is used only in the distribution line. It occurs in small sizes as compared to other insulators. It always places in between the line conductor and the earth. The insulator works as a protective device when sudden fault condition or voltage change occurs in the line conductor. Next, we are moving to the advantages of insulators. The insulators prevent the flow of electric current. The main purpose of insulators is to prevent electric current from passing through them. This allows control over the flow of electricity. The insulators protect live electrical components. Insulators protect live wires, parts from accidental contact, which could cause electrical shock or any equipment damage. The insulators help maintain high voltages. Insulators can withstand high voltages without breaking down. This allows electrical systems to operate at high voltages. Insulators help in reducing the energy losses. Insulators reduce energy losses that occur due to electric current flowing through resistors. This improves efficiency of instruments. Next, we'll move to the disadvantages of the insulators. So they have limited operating voltages. Many insulators have relatively narrow operating temperature ranges. They can lose their insulating properties at high temperature. There may be some surface contamination issues. Dust, moisture or other contaminants on the surface of the insulator can reduce their effectiveness over time. This requires periodic cleaning. There may be breakdown at high voltages in case of the insulators. Insulators can eventually break down and allow current to pass if the voltage across them exceeds their breakdown voltage. This limits the use of the insulator. Insulators are prone to damage. Some insulators are mechanically fragile and can be damaged easily, especially in harsh environments. This requires replacement. And due to the maintenance, it may have some additional cost in case of the insulators. Now we are moving to the applications of electrical insulators. The electrical insulators are used extensively. They are mostly used in offices, homes and public spaces, in equipment and appliances where the passage of electricity is not required. Electrical insulators are used to prevent high voltage from being generated by electrical devices. Human skin will conduct electrical charges if it comes into the contact with any active exposed wire, and current will be felt. In order to stop the flow of electrical charges, insulators are placed over exposed wires. So learners, so now we can go for the differences of conductors and insulators. So already we have come to know that in case of the conductors, they allow electricity to pass through them, which is not allowed by the insulators. In case of conductors, they have existence of lots of electrical charges on their surface. In case of insulators, we don't have electrical charges on the surface of the insulator. In case of conductors, the conductors don't store energy, but in case of insulators, they can store energy. In case of the conductors, their thermal conductivity is high, but in case of the insulators, their thermal conductivity is low. In case of conductors, its resistance is very low, but in case of insulators, the resistance is very high. So already we have come to know different examples of conductors and insulators. So let us go through some quizzes again on insulators. So our first question is, which group among the following is insulators? A. Silver, copper, gold. B. Paper, glass, cotton. C. The human body, wood, iron. D. Glass, copper, paper. The answer is B. Answer B contains all the insulators, that is glass, paper and cotton. They are good. They are examples of good insulators. The second question is, the band gap between the valence band and conduction band is the measure of A. The conductivity of the material, the polarization of the material, surge density, or ease of ionization. So the answer is, it is the conductivity of the material. The third question is, which of the following is the main field of application in case of pin-type insulator? Distribution system, transmission system, transmission and distribution system, EHV, transmission system. So the answer is distribution system. The question 4 is, a transmission line consists of 9 discs of a suspension insulator in each spring. What is the operating voltage of the transmission line? The options are 11 kV, 33 kV, 66 kV, 115 kV. The answer is 115 kV. Why? For different values, it doesn't need to use different suspension insulator. Strength of insulator can be increased just by adding extra disc of suspension insulators. For 130 kV transmission line, 9 or 10 discs are required. Question 5 is, suspension insulators are made up of, our options are glass, porcelain, statite, epoxy resin, and the answer is porcelain. Dear learners, hope you have enjoyed this session on conductors and insulators. So we have come to the end of this session. Let us quickly summarize the topics that we have discussed as follows. Conductors allow flow of electric current through them, while insulators obstruct the flow of current. Conductors have lots of free electrons, which is the main reason for conductivity. Insulators don't possess free electrons, hence they have poor conductivity. Conductors have overlapping of conduction and valence band, while there is a high band gap in case of the insulators. So thank you.